Hi everyone. So, we are on this topic radiographic testing, and in last few lectures we have seen the different aspects of this particular technique, and we have also learned about how the image is formed on X-ray film. Okay. And then in the last lecture we talked about the different kinds of intensifying screens which are used to enhance the quality of the image. Okay. So, in today's lecture also we are going to take up this image quality again, because there are few more things particularly related to the X-ray source which will control the quality of the image, and that is what we are going to talk about in today's lecture. Okay. So, the quality with regard to the film properties, how the film properties control the quality of the image, all those things we have seen before, as I said. So, today let us see what are those parameters related to the X-ray source which will control the quality of the image, and what can you do to get the best quality. So, let us see what is image quality and how it is affected by the X-ray source, and then we will see what can be done to get the best quality image out of an X-ray machine. If you do not have the right parameters or the right focal spot size in a given X-ray machine, then the image that you get will not be very sharp. Okay. The quality of the image will not be at its best. So, this inability of the instrument or the X-ray radiation to reproduce the best quality image is known what is called as unsharpness, sometime which is also called as penumbra. So, this can be defined as the inability to properly reproduce the boundary of an object. Or the minimum distance between two objects that can be resolved. For example, if you have an object and if you have a sharp change like this, a sharp 90-degree change in the curvature or in some section of the object, then if your X-ray machine is not able to reproduce this sharp boundary properly, it will give you a diffuse boundary like this instead of this sharp change. So, this sharp change will look as a gradual change like this. Okay, so, that means you had this boundary where there was a 90-degree change, but when you see the image you do not see that sudden change, rather it comes out as a gradual change. Okay. So, this inability to reproduce this boundary properly, as we defined just now, is known as the unsharpness of the image. Okay. And this primarily happens due to the focal spot size of the machine. So, X-ray machines come with a focal spot which is having a finite size, and it is not a point source, right. So, when you have a focal spot with a given size, it will act as a multiple point source. Okay. So, if you have a point source like this, then you know that there is only one X-ray source from where all the X-ray beams are coming out, and they will go through the sample and produce the shadow of the sample or the image that you see on the X-ray film. So, if this be the point source, and let us say you have an object like this and there is a feature like this on the object. And if it is a point source, so you know that these rays are coming from only one point and going through this object and the boundaries of the object, and as a result when you keep the film here, you can reproduce the boundary exactly like this. Okay. So, this is actually the density plot that you see on the image, because you are collecting the photographic density from different parts of the object, and that is what is being shown on the X-ray film image as contrast. Okay. So, if it is a point source, there is no difficulty in reproducing the boundary of an object, as you could see here. But if it is a finite size source, then because of that given size, it will act as multiple sources. Okay. For example, if you have a source like this, so this has a given size. Okay. So, this is the spot size f. So, it has multiple points because it has a certain size. So, if you now take the same object and image it using this particular source, which is not a point source, then it will look like this. So, now the X-rays will come from different points. Let us say we will just take up 2 points from here and from this point also for this boundary. Similarly, for the other boundary from this point also it will come, and it will come from the other points also like this. Okay. And as a result of that, when you see the density plot on the film, this sharp boundary will appear as a diffused one like this. So, you will not see that sharp change which is there in the boundary, rather it will appear as a gradual change like what we have seen in this case also. So, this is due to the size of the X-ray source or the focal spot size. Okay. And this particular phenomena is known as unsharpness. And since it is related to the geometry of the source, it can be defined by a geometric parameter. So, if you simply take the ray diagrams now, you would be able to get an expression for this. So, let us say this is the source with a spot size of f, and then you have the object. So, again because of its size, it will act as multiple point source like this. So, the rays will come from multiple points, and on the film this is how the density data will appear. So, let us say this is A and this is B. So, since the rays are coming from multiple points, for point A you would see, if it comes from 2 points, you will see for a single point of the object you will get 2 different points on the image like this for point A, and similarly for point B you will get more than one point on the image. Okay. So, this particular phenomena, as we have already defined, is the unsharpness. And it can be easily found from this geometry, and since it is related to the size or the geometry of the source, it is also known as geometric unsharpness. Which is indicated as UG. So, this is the UG, and if you consider this ray diagram and the geometry over here. So, if you consider this triangle, this one and the other one, this one. So, the height for the first triangle, this one is the distance between the source and the object, which we will call as L naught, and the height for the second triangle is the distance between the object and the film, which will indicate as small l. Okay. So, now if you apply the triangle rule here for these two particular triangle, then you have base by the height of the first triangle will be equal to the base, which is f for the second triangle, by the height, which is L naught. Okay. So, from here you get an expression for u g. So, this depends on these 3 parameters. So, from here you can see how the quality or the sharpness of the image will depend on these parameters, and when you vary one of them, the quality or the sharpness of the image will vary. Our objective is to get the best quality image, and therefore, this u g has to be minimized. Okay. And according to this particular equation, we can see that u g can be minimized if you could minimize f, keeping the other two same. For a particular focal spot size, you can either minimize L, that is the distance between the object and the film, or you can maximize L naught. Okay. So, these are the 3 choices that you have to minimize the unsharpness and get the best quality image. Okay. Now, for a given machine, once you have a particular equipment, for that the spot size is fixed, because every machine comes with a particular spot size, and you have to use that to get all the images. So, that means for a given machine your f is fixed, for a given source and a given equipment. So, that means the other 2 parameters that you have to play around are these 2 distances L and L naught. Okay. So, if you maximize L naught, that is the distance between the source and the object, then your u g will be minimized. But the problem with that is, if you increase the distance between the source and the object, the intensity is inversely proportional to the square of the distance. Okay. So, you will compromise with the intensity. Okay. If you increase the distance, for example, by double, your intensity will decrease by 4 times. Okay. So, that is why it is also difficult to change this distance between the source and the object. So, that leaves us with this distance, the distance between the object and the film, to change it and minimize it, to minimize the unsharpness. Okay. So, that means the film and the object, the distance between them should be minimum, and it will be best to keep the object and the film in that case in intimate contact. Okay. So, that this distance L naught, sorry, this distance L is minimized. Okay. So, in this case, when you keep them in contact, L will be simply the thickness of the film T f plus the thickness of the sample or of the object T s. Okay. So, since the film and the object are in contact, this is also known as contact radiography. Right. So, this is how for the same for a given spot size, by keeping the film in close contact with the object, the unsharpness can be minimized. And that is why the sample is kept right over the film with the help of a sample holder, which I am going to show you a little later. So, that this distance between the object and the film is minimized. So, if you talk about the spot size, the conventional radiographic sources that you have the size generally varies from 1 to 4 mm. Okay, so, this is the size range in which the machines come, which are generally used for industrial radiography. And if you want to have a smaller spot size, then you have to go for these mini focus instruments, in which the spot size is in the range of sub-millimeter from 0.2 to 0.5 millimeter. Okay. If you want to go to further down and want to get a source which is almost like a point source, in that case you need to go for a micro focus unit. Where the spot size is in the micron range from 1 to 50 micron. So, this kind of mini focus or micro focus sources may be needed for certain purposes, for certain special requirements, but the commonly used ones that we use for industrial radiography will be having a finite size like this. But the point source will have its own advantages, because it will not give you any unsharpness in the image at all. Okay. And it will also allow you to magnify the image. If you want to magnify the image, in this case, when you have a finite spot size, okay. So, when you magnify the image, means the distance between the film and the object also increases. So, for a finite source, we have already seen how the image is formed. So, in this case if you want to magnify the image, then you have to increase the distance between the object and the film, and as you could see from here, if you increase this distance, then this unsharpness is also going to increase. Okay. So, that is why in this case there is no question of magnification, but on the other hand, if you have a point source, then in this case there is no question of any unsharpness. So, even if you increase this distance, it will only get magnified without the image quality being compromised. Okay. So, for point source or for micro focus, you have an advantage of magnification. And this is known as projection radiography if you magnify the image. And this magnification mg is given by these distances. Okay. So, this is the advantage that you have. The other advantage that you have in case of point source is what is known as depth of focus. Which means up to what depth can you focus the sample for a single exposure. So, if it is a finite source, finite size source, then and if you have an object like this, so if you have features like this which are within this field of view, they can only be focused. Okay. So, you cannot really focus two features together, one which is at the top and if another one is there close to the bottom. These two cannot be focused together for a finite size source. So, it has a limited depth of focus. On the other hand, if you have a point source, since from the point source the rays are going to come like this, whatever comes within this this region will be focused. So, you can see from almost from top to bottom of the sample, you can focus in a single exposure itself. Okay. So, this provides you a better depth of focus compared to a finite size source. So, that is the other advantage that you have if you use a point source or a micro focus source. Okay. So, when the image is magnified by using point source, the other name for that is X-ray microscopy, because this magnification comes into picture when we talk about microscopy, where you have lenses through which you can magnify the image. Okay. So, in this case also, since the point source allows you to do it allows you to magnify the image, this is also known as X-ray microscopy. Okay, so, this is how the size of the focal spot will control the quality of the image. So, with this we come to the end of this particular lecture today. Throughout this whole week, we have been discussing about radiographic testing. So, it will be good to take a summary of what we have learned in this week. So, let us take the summary of this week's lectures. First, we learned about the basic principle of radiographic testing. Where we saw that it is primarily based upon the absorption of X-rays which is due to matter and X-ray interaction. Then we derived an expression for this absorption phenomena, which is like this. Okay. And as I said before, this forms the basis for radiographic testing. Okay. And this matter X-ray interaction, with regard to that particular phenomena, we saw there are different atomic scattering events which lead to the absorption of X-rays, and in this we have seen different types of atomic scattering events, and we have also discussed about their contributions to radiographic testing. And once we understood the basic principle of radiographic testing, we discussed about the image formation, and in this we saw that you first need an X-ray source, which is nothing but X-ray tube, and about that X-ray tube also we have discussed when we discussed in the beginning about the generation of X-rays. And the other thing that you need for capturing the radiographic image is the X-ray film. And we have discussed in detail about the X-ray film, its construction and its constituents, how it is made and what is the main constituent in these X-ray films, that also we have discussed. Then we talked about the characteristics of the X-ray film, like the photographic density D, the contrast CS, and we also saw that for every film there is a film characteristic curve, and from this curve you can again derive some film characteristics or film properties, and those were the gradient G, the film latitude, and we have also seen how to calculate film speed from this characteristic curve. Okay. And we have seen that there are primarily two types of curve. One is S-shaped and the other one is J-shaped. In the J-shaped category, we also saw that there are three types of films 1, 2 and 3, and in the S-shaped category there is type 4 film. After that we talked about intensifying screens, the basic purpose of which is to filter out the scattered radiation which is not desirable for forming the image, and also to enhance the efficiency of image formation. So, these are the two primary objectives of using an intensifying screen. And we saw that there are two types of intensifying screen. One is metal screens and the second one is fluorescent salt screens. After that we discussed about image quality. And the parameters which control the image quality, and with regard to those parameters we learned that certain parameters come from the X-ray source. For example, the focal spot size will affect the quality of the image, and with regard to that we learned about an aspect called unsharpness, which comes due to the finite size of the focal spot of an X-ray source. And the image quality would also depend on the properties of the film and the parameters which influences the quality of the image with regard to the film, that also we have discussed. So, with regard to the film, as we have discussed, you need a high G a high value of gradient and you need fine graininess. Okay, so these are the things that we have learned so far about the X-ray radiography technique, and the rest of the things that we have for this particular technique will be taken up in the future lectures. So, for today this is all I have. Okay. So, I am going to stop here today. Thank you for your attention.